اتفضلي انتهاء.
السلام عليكم ورحمة الله. اللهم صل على سيدنا محمد وعلى آله وصحبه أجمعين. معكم ابتهال، عضو من أعضاء منصة فوتون. نرحب اليوم بدكتور سلطان حسن. عنده حيتحدث معانا إن شاء الله. ودي مقدمة عنه: extracting all information from future surveys with deep learning. Dr. Sultan Hassan, he's from Sudan. He did his PhD in the University of Western Cape, South Africa in 2018. He held several prize fellowship, including the SKA fellowship in South Africa. Then he moved to New Mexico State University, and he worked also as a fellow until the 2020 years. And then he worked as a researcher at the Center of Computational Astrophysics in the Flatiron Institute in New York till 2022. Recently, he's working in a NASA Hubble Fellow at the New York University, and he started from January 2023. Dr. Sultan also is working in intersection of astrophysics, cosmology, and machine learning. And he have also some expert, including cosmic dawn, reionization, and small-scale intracellular mediums, galaxy formation, and large-scale intensity mapping technique. دي مقدمة صغيرة عن الدكتور، وإن شاء الله نتمنى نعرف معلومات أكثر عن التخصص ده إن شاء الله. ونرحب بالجميع وندي الفرصة للدكتور إنه يبدأ. مرحبا بك دكتور حسن.
طيب، شكرا جزيلا للدعوة وللتقديم ده. شايفين السلايدز دي؟ good.
أيوة واضحة. أيوة
good. طيب في البداية زي ما قلت متشكرين على الدعوة ودي حاجة يعني انيشيتيف ظريفة جدا ونتمنى يعني انه تكون مفيدة للجميع والواحد يحاول في الفترة دي يعني في الساعة دي يقدر يتكلم عن بعض المشاريع والحاجات الواحد كان شغال فيها في الفترة الماضية. قبل ما أتكلم عن الموضوع اللي أتكلم عنه، أنا هتكلم عن حاجة معينة بس في الانترست بتاعي، لكن I have a very broad interest as يعني ابتهال was saying. I work mainly on high redshift early universe astronomy and cosmology, so I'm very interested in reionization and cosmic dawn. I work in the source population and galaxies, black holes, how to model the emission lines and the absorption lines. I worked intensively also in the star formation models development, how the interstellar medium and the cosmological simulation interact. I use similar techniques like hydrodynamic simulation and semi-numerical models and analytical models. I think a lot also about the early universe physics like primordial fluctuations. I try also to connect experiments going from radio to optical to infrared. And I work a lot on outreach activities. So I'm active member in the National Society for Black Physicists in the US. I recently joined the Arab Physical Society, mainly actually their headquarters in Egypt. And recently I started the Sudanese or the Sudan Next Astronomer Program, which is an initiative that to train the next generation of astronomers from Sudan. So the basic idea is we try to help students how they apply for graduate positions, where to find the opportunities, whether they can get a research experience, and to help them to get nice recommendation letters and interact with the community. So I think this is one of the things that is really missing. And we already started. We have a very nice set of students, 6 students already working on. We meet every 2 weeks. So anyway, I might be asking some of you actually to come and contribute to this at some point, but it's a very, so far it's been very successful, I guess. And what I will talk about today is basically the artificial intelligence part. And yeah, so feel free to email me if you want to chat about any one of these topics, and if you are interested to help with my SNAP initiative. So this is our story, right? So let's start. So our story, it's known, right? Like we know that the universe started with the Big Bang, right? Everything was ionized, right? The Big Bang was a very hot, dense state of matter, right? Exploded. Everything was extremely ionized after that time. Then, you know, that's the beginning, right? Then we have, as the universe expands and things cool down, recombination starts, which is basically, this is the first time that the hydrogen and the electrons combine together. They recombine together to everything gets neutral, and then we enter this dark ages. So we don't know anything what happened in these dark ages because we only, as astronomers, we see through light, right? So we don't know what happened during this time, but there are many theories talking about what could happen during this interesting time. Then after that, we know the first generation of stars and galaxies come in. They started to emit light. The universe was extremely neutral at that time. And they started to emit light. The light went into the intergalactic medium, which is the medium between galaxies, right? And this is like different dots of different galaxies. And each galaxy started to emit these lights, right? And the light started to ionize the medium again, and this is what is called reionization, which is because the universe was ionized in the beginning after the Big Bang, and then when we have the first generation of stars and galaxies, or we don't even know what the first generation of these luminous sources, by the way. All we know is that there is some light coming. We know maybe they are stars, maybe they are black holes, maybe they are other sources we don't know yet. I mean, people actively working on this regime. But what we know is that there are many evidence that reionization happened, and our understanding is that the photons coming from these earliest generation of stars, they started to ionize the gas in the universe. And then after the first billion year, right, after the Big Bang, we became fully ionized. That's actually one of our reasons to exist, even because if we in a very highly neutral universe, it's very hard to have many conditions for many life in many area in the universe. But anyway, so that's the first billion years. And then we started to evolve, and up to now, the universe about 13 billion years, and we structure formation grows, and we have now all these fluctuation of galaxies. So this is a very this is the picture according to the standard model of dark energy, dark matter, and cold dark matter scenario. It's called lambda CDM, and it's a very successful story. People work on different modification to this to try to address other issues, but roughly, broadly, this is our story, and there are many observational evidence for why this might be happening, including the cosmic microwave background and other things, right? So this is the timeline for this experiment, and that's just to address the question I have, right? Like, what actually, like, why I'm very interested in artificial intelligence and why we really need that, right? We need this for many reasons. This is the timeline for experiments coming from NASA and from other experiments. We already have DESI working, SDSS working. 2022, right? We had recently the successful launch of James Webb Space Telescope. Then we have the Euclid also launched in July. And then this is the planned timeline for the experiments. You have a Spherix mission, you have Roman mission, you have extremely, I don't have the time to go into different details, and the SKA coming to South Africa and part in South Africa and part in Australia. But the basic idea, what is happening here is that all this timeline of these upcoming experiments and telescope, they have very unique capabilities, right? So they have very high sensitivity. So they are able actually to detect more faint sources. And they have very big, large field of view. So they would be able to probe different scales and something that we were not able to do before. And And with that comes the challenge that our current theoretical models and theoretical techniques and analysis we use in astronomy, most likely they will fail to address these upcoming experiments and the observation coming from them. So we really want to be able to look for new, as we have a new generation of surveys coming up, we should prepare for this, and we should really have our new generation of models and technique. So that's basically what is happening. That's basically the main motivation for this. So the question I'm trying to answer here is that, right, theory is beautiful. You can have your own theory and you have your stories and guesses and stuff, right? But without connecting to the observation, it's just a speculation, and it's not really. And one of the basic ideas for the scientific method is to try to connect to observation and try to test the theories you have, right? So the question here is that we have observation. Let's say the observation for anything. I mean, I'm not really talking about any specific observation, but let's say you have your telescope, you observe all galaxies in the universe, the source count of these galaxies, or you observe their emission, or you have this big map of all observables you look at in the universe, and you get your data and you get all these large scale images. Then the question here is that how do you analyze this, right? Like, how would you extract information from there, right? So to answer this question, I think this is a very important question. Everybody probably in every field in physics probably should ask themselves this question, like, how do you really, if you have any observation or measurements, how do you really get the maximum information out of there, right? And that depends mainly on how you do it, right? So I think the first thing is that obviously you need to have a very improved and very good theoretical models, right? Like, if your model does not account for all the physics in different things, like different part of the universe, it's extremely hard to extract all the information, because what we do basically, we try to compare our models to the observation, right? And the more like, if your model is very rich and accounts for many things, that's very nice. However, we have challenges in this modeling, right? So this is a snapshot of the universe, right? This is coming from, I made this using TNG simulations, one of the state-of-the-art cosmological hydrodynamic simulation. This is a snapshot of the universe. Each dot you see here, this is what we simulate, our current thinking of how the universe look like. Any dot you see here is a part, it's basically a galaxy, right? So the medium between these galaxies and the gas between all these galaxies, we call the intergalactic medium. And as you see here, this is all like about 6 megaparsec size slice of the universe. And to know, just for your reference, is that 1 parsec basically is about 3 light years, which is the time for the light to travel. Of 3 years, or it's about 10 to the 16 meter. So it's a very, for us, it's extremely huge, but for the universe is nothing, the parsec, and it's 1.5 megaparsec even is nothing, because the universe is extremely large, right? So this is the first scale that you might get when you get this observation. If you zoom in into one of these galaxies, right, now you're going from mega parsec to kiloparsec scales, and this is what you can see here. This is one of the spiral galaxies in these simulations. You zoom into that, and then you see in the scales of kiloparsec scale, you cannot see it by the eye if you have the full universe, right? You need to zoom in, right? And then when you zoom in, you find this is something we call the circumgalactic medium, because it's the gas between around galaxy, right? And this is really holds many important physics, right? Like about how the feedback happen in galaxies, how the evolution of galaxies evolve, how galaxies evolve through time. It has many interesting stuff here. So that's a different scale. You talk about kiloparsec, right? If you zoom further and you go to 1 kiloparsec scale, which is now you are approaching the parsec scale, then you will go to the interstellar medium, which is the medium where the gas and the dust between stars inside galaxies, right? And this is very important thing, the interstellar medium, where actually it's where star formation happening. where many of the interesting physics, astrophysics is really happening, right? So you have that. So in our way to model things, it's extremely hard. Probably I can say this safely, no model in the field now would be able to capture this fine resolution of the interstellar medium, as well as evolving things for large scale simulation. So that's a big challenge. So we need to be able to do this. And this is maybe with machine learning, we would be able to do that, but or maybe if quantum computing comes, but that's a very challenging task. So we need to be able to model all this scale to extract the maximum amount of information. So that's the first point. The second point we want, right? We want to be able to create highly synthetic observation, right? Like you have your simulation, but what we simulate is not the universe, right? So what we simulate, we observe what we observe, but what we simulate is not the universe, right? So how would we make assumptions, we make our models and simulation, but then how would we actually make them look like the universe, right? We need to be able to do that. And that depending on the observable you have, and it's extremely hard and challenging task because now it depends on the experiment, it depends on the many techniques. I can give you one example to show here. This is one of the signal simulation that we did run a long time ago about reionization, how the ionized bubble grow from different galaxies and sources. And you have the signal here by the left-hand side, right? And you have different experiments like SKA coming to South Africa, also HERA in South Africa, LOFAR in Europe, right? You want to make this signal look like what SKA or HERA or LOFAR would see. And you can look them up. I don't have the time to explain differences between these different experiments, but people believe that SKA will have a much larger baseline and it will be able to see the signal much better than other experiments. But what is interesting here is that this is the thing that you need to account for. You need to be able to take the angular resolution of the experiment, because now depending on the dish size, depending on how many dishes you have, your signal in the sky will be very different, right? So now that's why, like in the SKA, you kind of still see the fine small scale structure after you apply the angular resolution. But for HERA and LOFAR, you can't really see the small scales. You only see the large scale because everything will be wiped out because they don't have the sensitivity and resolution to detect these small tiny bubbles, right? So that's for the angular resolution. But then you need to care about the thermal noise too. And then you need to add them together. That will give you much closer to that. But that's also the way that we do this, that based on many assumptions and many assumptions we assume, right? So then it might not be true. It's a very challenging task. One of the biggest ones that people fight for all the time is the foregrounds, because when you observe, there is contamination coming from your own galaxy, right? From the same Milky Way, there is foreground emissions coming, and there are emissions from extra other sources in the universe, right? And actually, this foreground magnitude is actually a lot larger than any signal you want to observe. It's probably 4 orders of magnitude higher. So if you take one of these signal and you add their foreground, and then you look at what you have in the left is the signal without foreground, and on the right is when you add the foreground, basically the signal gets destroyed completely. And this is what we basically observe. What we observe is the signal on the right, and then we want to be able to recover our signal from the models, and we want to get the clean physics, right? Because once we have the clean signal, we now relate to the cosmological parameters, to the astrophysical parameters, we can do lots of fun stuff in our physics, right? And we can constrain our models and stuff. But that's extremely hard. You have this signal, you want to recover that signal out, and you have all this contamination. So this is extremely hard problem, right? The last thing, so this is how the way that I think about it. Like if you have observation, you want to get all the information out. First of all, you have to have improved models. You have to count for different scales. Second is you need to have a very, very efficient way, an accurate way to how to generate synthetic observation. The last one is you need to be able to develop efficient tools, right? And this is where machine learning comes, right? That can constrain these improved models. And and this is the challenge. The challenge is that with all these surveys, if I give you a large scale map, right? Let's say the map has 1,000 pixels by 1,000 pixels, right? Like 1,000 by 1,000. There is no way with the traditional statistical methods we would be able to analyze this map. That's why we need machine learning here. There are many things which I will explain in a second, but I think one of the problems is that because the observation coming towards large scale, high resolution imaging and fields, we need to be able to have different methods to do that, okay? So in my talk, I will assume that my models are extremely improved. I have the best model ever, which is wrong, but let me assume that. And let me assume also that I am able to generate highly synthetic observations. So anything that I say that next is just I'm trying, okay, my models are good. I know how to do that, which is wrong, but let's assume that. And let's focus on the last task because each one has its own challenges and how to develop tools to perform inference and constrain these improved models, right? So this is machine learning, right? But in the beginning, let's try to address the elephant in the room because there are some people might not really believe in machine learning, right? So let's address that. So the question here is that does it always work, right? And we have now great progress in machine learning, right? Now we have like these transformers where we have ChatGPT where you prompt a model, it's a large scale language model. You prompt the model can answer any prompt and any text you ask, right? So it's a very, very powerful model. We have DAL-E, right, where it's basically image generator conditioned on text. So you ask it, oh, I need a picture for a laptop or a dog or something. It will give you that picture, and depending on your prompt and expression, right? So I wanted to try that. And then I asked DALL-E, right, to generate the cosmic microwave background. I hope that you know this, but that's basically when you observe the universe in and then you extract all the sources, the remaining background in the microwave band. It's one of the things actually there is 2 Nobel Prize winners because of the CMB. It's one of the most important observation in our universe, and it supports many of the physics I was talking about earlier about the Big Bang and all that, right? Because it's just the first thing about the Big Bang, right? So I asked DALL-E, okay, let's generate the cosmic microwave background, okay? And then you ready? Okay. So this is what I get, right? So it's interesting, right? You ask the model, you want the cosmic microwave background, right? But the model basically brings you a picture of a microwave in a table, but in a cosmic background, right? So a microwave flying in the cosmic background. And the question here is that, does it work or not, right? So if you think about it, maybe you say, well, maybe machine learning doesn't work at all. I mean, I didn't ask the model to do this. I wanted the cosmic microwave background, but then it brought microwave on a cosmic background. But the question interesting here is that if you bring an artist, right, with zero physics, like an artist that doesn't know anything about physics, and you ask them, draw the cosmic microwave background, only the information you give them is just cosmic microwave background, they would probably do the same. They would draw a microwave in this cosmic microwave. So I think machine learning, when you hear it doesn't work or whatever, it depends mainly on the information and the knowledge you give it to the machine, right? So if you don't give the models and the machine learning models enough information, they might totally fail to give you the expected results. Okay. So why do we need this, right? So the traditional way for these large scale surveys, right, is we don't have enough memory. Our supercomputer is very low. We need to find way to analyze data, right? So this is one of the example what people do. What people do basically is that you have 2 different fields. This is one field in the left and the right. This is just how the density fluctuations is evolving in the universe. And we have 2 different models, different thinking. People think it's more disconnected. Some people say it's connected. There are many scenarios about this. but they are visually really different fields. And the leading way to analyze these maps, because we don't have the memory and we don't have the computing power, what we do is we look for summary statistic to analyze this map, right? And the summary statistic could be anything. It could be the PDF, it could be the histogram, it could be anything. One of the leading summary statistic, which is the power spectrum, what you see in the right. And the power spectrum basically is the average of the image in the Fourier space. So you take the image and you transform this image into Fourier space, and then you basically calculate the modes as a function of the wave number. What you see here, these are completely different fields, but if you look at their power spectrum, which is the red and the blue, they're exactly the same. So the power spectrum basically exactly the same. So the power spectrum does not really capture this information. And many analyses that we have, we want to compress the information on this large scale. So then to be able to process them, because we don't have like large storage and we don't have like supercomputing power, but we are losing information. We are losing information because we are working with the power spectrum. Power spectrum cannot really discriminate between two fields. And therefore, we need to work at the field level. We need to be able to work at fields. Otherwise, if you compress the fields into different representation, then you might not be able to extract all information. So that the first thing is to be able to work at the field level, okay? So in general, let me talk about the general two branches in machine learning. So this is the Bayes theorem. This is one of the Bayesian theorem. This is one of the cornerstones actually of statistics and how do we really extract information from observation, because it's basically the probability of the model given the data is equal to the probability of the data given the model over the prior range for the model. And if you have a machine learning model, and this is what we call, so in the left-hand side, this is the posterior distribution, and in the right-hand side, this is the likelihood. And if your machine learning model really targets the posterior distribution, then this is we call discriminative model. And if your model really target the likelihood and you're trying to model the likelihood, then it's a generative model. And I think the current direction now in machine learning towards the generative model for many reasons, right? One of the biggest reasons is that if you have the posterior distribution, you cannot get the likelihood. But if you have the likelihood, you can easily recover the posterior distribution. So learning the actual likelihood, what is the probability of the data or the observation we look at given your model is more interesting, and it's more interesting than the posterior distribution. Okay. So now let's talk about different examples of things that I have done with discriminative and generative model. So this is in this work, what we try to do is that we want to study this is a posterior. You're basically going directly to the posterior distribution. And then we wanted to ask, what is the probability of AGN or galaxies? So AGN and galaxies, they are different sources of emitting ionizing photons. And we have these ionized maps in the large scale universe. And then they have different topology and morphology in these maps, whether reionization really driven by these black holes, which is active black holes, we call them AGN, active galactic nuclei, or galaxies, right? So, and we don't know, this is a big debate in the field. We don't know whether really reionization happened due to AGN or galaxies. But then the way you do this is that you can basically do that with the machine learning, right? And one of the actually leading techniques now to extract information from maps and large scale maps is called convolutional neural networks. It's achieved the hard performance. There is no way you have I don't think so far there is any method can beat and outperform CNN want to recover anything from maps. So any maps you have, you don't know what to do, you plug them into CNN, it should work. And the way that it works is that you have an input, right? You design your neural network into different series of neural layers, right? And then you're trying to compress the information as the image propagates through the network, and then you want to predict only two numbers, either galaxies or AGN. So it's a classification problem. And the whole idea of training is that you want to find what is the optimal filters, right? You have all these different filters and different layers. You want to find out what is the optimal filter can maximize your prediction, right? So you plug in the image, it tells you this is AGN, but you know it's galaxy. So then you try to correct for that error and you try to change the filters and the layers in the network so then they can maximize this predictions. And you see now, if we want to see this as a function of the training steps for different, this is the Z here records different lines in the universe, different time in the universe. And then you see here, we are quickly able to go, this is the accuracy, which is how many images being recognized correctly. And we are able to get the 100 accuracy very quickly from the few first training steps. So anyway, so that's good. It's very exciting. We are able to do that. We have this tool now. When the observation comes in the future, then we would be able to tell whether this is coming from AGN or galaxy, which is something can help many of the debates we have in the field. Other thing that was done by my first master student from South Africa, where we were looking at something else, right? We know, like, measuring the neutral fraction of the universe, right? As I showed you in the beginning, the universe was extremely neutral and then it started to ionize gradually, but we don't know actually what is the actual neutral fraction. There are many different probes for this, but we are hoping actually by observing the actual distribution of the ionized bubbles in the universe, we might be able to constrain this parameter. So then you have these simulated maps, and then you make mock maps. This is what I'm saying. I'm assuming that I'm able to do that. So you add the foreground, you add things, so that the signal will be very different. And we want to see what the probability of the neutral fraction given the maps. And we look at this, how the prediction looks like. So this is here your X true, which is the H1, the neutral hydrogen. What we know, the true value from the simulation, and this is what the machine learning model predicts. And then you see there is a strong correlation between them, which means that we are able to predict the correct neutral fraction for all the maps. And if we test with simulated data, mock data set, we are able also to score high accuracy with that. So that's exciting. We have a different way to do this. Now I want to talk about the generative models because it's more, I think it's one of the more exciting directions, and which is we try to model the actual likelihood. Okay, so this is one of the work that my master student South Africa is doing now, which is basically a paper accepted to ICLR. And we're trying to see, one of the problem with these reionization simulations is that it's very expensive, right? So how do they work? You start with the density field, and the density field, usually we populate that from a Gaussian field or from anything. You have a density field. You apply your favorite recipe to find the sources, which is here, your sources, right? And then you apply radiative transfer, which is basically tracking the photons and how they ionize the medium to get the ionization field, right? So it's a multi-step in the simulation. And this is very extremely expensive. If you look at the actual simulation timeline, 70% of the simulation timeline or 80% of the simulation timeline is only about finding sources and applying the radiative transfer. But this is going to be very hard for us. When we have the future, we need to be able to generate quickly different realization, and then we want to have a very efficient tool. So then we have, for any density field, we should be able to get the ionization field very quickly. And that's why we are interested to see how do we emulate the behavior of radiative transfer on large scale. And we want to ask the question here, what is the probability of the ionization field given any density field we have? And if so, then we emulate the behavior of the radiative transfer, and we would be able to extract much more information, because now we are able to generate things much more efficiently. And the way you do this, there are many ways to do this, but that's basically one of the successful architecture in generative models. It's called UNet because it looks like a U. And the basic idea is that you plug in we tried two different strategies. So the first strategy is model 1, whereas you basically plug in the density map to try to recover your ionization map. And you train the model to do that, and it's somehow successful. I can show you the results. in a second. And we tried a different model. So the first model is deterministic, so which means that each density field would correspond to only one realization of the ionization field. So it's a one-to-one relation. But we know this is not true because in the universe there is many variances, right? There is the cosmic variance, there is the fluctuations on large scale. So we cannot, we know that it's not only one realization, there are many realizations for the same density field. So then model 2, what we try to do, we try to make the model more probabilistic, not really deterministic, in a sense that when you train the model, you plug in your density field, but then you adding either white noise or a noisy the corrupted version of your ionized field during training. So then you can basically show the network that you have some noise propagated into the model. And because we have this noise now, you need to have some protocol for testing. So the basic idea, you plug in your density field, you plug in with that a white noise, and then the output of the network will be one realization, which is one of the ionized field. And then you recycle that into the model. And as you see, through testing, the ionized bubbles get very large. And now that's why you have different realization for the same input. And then you can stop your recycling and recurrent testing into the network when you are actually, you get a very good result with the target that you're trying to get. And if we now compare the different models, the density field and the ionization field, this is the true one. We see that model 2, because it's probabilistic, gets much more closer to the right field. And if we want to compare this at the level of the power spectrum, we see that model 2 really recovers the power spectrum much more nicely than model 2. Model 2 recover that, so the probabilistic model very wins. So now we have a way actually to emulate radiation transport or large scale, which is very, very exciting. I think, how am I doing on time, by the way? So I don't want to take much time.
I think you are fine.
I can go?
Yeah, go ahead.
Okay, so so the last thing, so there are two examples I want to share with you again with different generative models here, and I think one of them is diffusion models. So diffusion models, they are actually an amazing models because they actually achieve the state of the art in image generation, and we already have shown, and many people shown in the field, that it will really be a transformative tool in the upcoming surveys, and I will show you this now. So the basic idea for these models, why we are interested in them, because there is a website, nice website actually, called Papers with Code, and that you can go and type any task. It will give you different, it will give you the score and the accuracy, and it will compare that with different methods. So diffusion models, this is a data set. This is one of the nice data set. It's called CIFAR 10. And this is, it's a very interesting data set, right? So you have airplanes, you have birds, cat, deer, dog. It's extremely hard data set. And then you want to classify between them. You want to have a really good model to classify between them, or you want to generate them. And for doing this task, the diffusion models, they are the best ever model to do this. And if you take the first 5 models, 3 out of them different variants of diffusion models, and then if you look at the 10, there is already 5 out of the first 10. They are diffusion models. So they are very, very popular and very, very powerful. And they are recent, actually, like only 2 years or something back. So how do they work? Well, the basic idea, it goes, there is lots of equation and stuff there, but the basic idea for the diffusion models is that you start with your signal. Let's say any observation, a map, it could be one that it could be anything, but let's say you have 2D map, which is your signal here. It's a dog, right? And then you gradually add noise to this, right? So you add noise to this gradually, and you add noise till you completely get a noisy image, right? And then what happens here is to try to remove the noise slowly so you can recover your image, right? And people have shown this kind of technique is very powerful, right? Because now you will basically, you try to learn, you are trying to move your signal into complete white noise, which is the noise on the right, and then trying to slowly extract that out. That's the basic idea of the model. I wanted to do this, so then we have been looking for data set. One of the biggest probably data set in machine learning now in the astronomy is called the CAMELS data set, which is cosmology and astrophysics machine learning simulation. This is one of the simulation that is being run in the Flatiron Institute. And the basic idea is that we have different simulations like SIMBA and TNG, and I can show you different realization for these are the maps and the different observables you can get from these simulations. They are publicly available. You can just grab them and do any test you want. It's not only useful actually for machine learning. We have written many papers about quantifying the impact of different parameters because we explore different cosmological and astrophysical parameters, and you see that the model really captures diverse set of images, right? And because I'm kind of interested in H1, I took the H1 and I tried to apply this. So the question we have here is that we want to, for any given parameters, right? For any given set of parameters, we have these two parameters, which is cosmological parameters. This is omega matter, quantify the amount of matter in the universe, and sigma 8 is just basically the amplitude of the fluctuations. And we want to see, so for these given two parameters, can we generate fields or not? Can I have a generative model? Because this camel simulation that you have seen, it took them 1 year to generate this simulation. It's extremely expensive. And after 1 year, we only have like 1,000 simulation of these because they are hydrodynamic simulation, they are expensive to run. So if I have an observation and I want to really extract information from this observation, I cannot wait 1 year after the observation to get some sense of things, and maybe my simulation is wrong or whatever. So we want to see whether we can actually, for any given set of parameter, we can quickly generate maps or not. And this is the prediction of the diffusion models we have. So in the top is the camels. This is the true parameters. So for different set of parameters, right, you have different realization of how the neutral hydrogen distribution over in the universe. And this is our model, which is the H1 CDM, conditional diffusion model. And then you see visually, they look really similar. And if I look at the level of the summary statistic, which basically you take each map and then you calculate what is the histogram of these maps, and then you calculate the power spectrum from them for different cosmological parameters. And as you see, we kind of successfully able to recover all the statistics, even up to the second moment, because this is actually the variance of these statistics, right? So this is very exciting. So this is now we have a method. We don't need to run camels. We don't need to run any cosmological simulations or whatever. We have this machine learning model that is very fast. In a second, I don't have to wait 1 year. In a second, I am able to generate large scale maps with the correct statistics like BDF and power spectrum, right? Which is extremely exciting. The last thing I want to talk about, which is basically something I think it's very powerful, and something I think people should think about a lot to apply to their fields, because I think it's an extremely important method, and it helped us a lot, and it really has been transformative and made a revolution in our way of thinking in statistics. So that's called normalizing flows. So before I show you what it is, let me tell you what it does, right? So what you see in the left, this is fake faces. These are not real faces. These are fake faces generated by normalizing flow model trained on SALAB A dataset. So SALAB A dataset is a dataset for high resolution human faces, and people trained the normalizing flow model on them. And as you see, you are able to generate. When I saw this, I went, wow, that's an amazing. Like, you are having a model that is able actually to predict the dot in the eye. You see, like the small scale features and the large scale feature, and they are perfectly 100% decent looking humans, right? So I think that was very exciting to see, and it's a very powerful model. But it's not only powerful because it's very good generator, but it's also good because it does likelihood-free inference. One of the problem we have in inference, which is when you want to estimate parameters, right? the traditional way people do this is with Bayesian analysis, which is basically doing like MCMC, which is Markov, what is it called? Markov Monte Carlo, right? Markov chain analysis, which is basically you search in all the parameter space to find out what is the best fit to your data. But the problem with these MCMC's analysis is that most of the time you need to assume a form for the likelihood. So you need to be able to say what the likelihood is. And the challenge is that usually you assume Gaussian likelihood, but we know most of the signal in our astronomy and in cosmology, they are extremely non-Gaussian, right? And they are really skewed. So we cannot really assume a Gaussian likelihood. And this is called likelihood-free inference, because with this model, actually, you learn the actual likelihood free. You learn it for free. You get it for free. And once you get it for free, you can do inference for free. One of the nice packages that actually does this likelihood free inference, you can look it up. It's called ByDelphi, which basically in this paper, they show exactly that for a 6-dimensional parameter space, that's a very big dimensional parameter space, actually. The MCMC would require you to run million and million and million realization to arrive to this posterior distribution. But with this method, Delphi, they show that 1,000 simulation for them is enough to recover the same posterior, right? Which is extremely, really exciting to do. So in simple terms here, what is normalizing flows? I think it's just basically converting simple distribution to more complex distribution. And the magic happens with the change of variable formula. Everybody familiar with, we got that from first year, right? So you have a probability of X and you want to get the probability of the inverse of X, right? And then to go between these, the only thing that you would require is that your mapping, which is the F here, should be invertible. So then you can get this inverse, right? And should be differentiable because you need the Jacobian in changing parameters, right? And if you are able to do this mapping to be invertible and differentiable, then you're done. So the basic idea, you assume a base density, which is a simple density called the Gaussian field. And this Gaussian field or any standard base density, you apply a series of neural networks, right? You apply a series of neural networks with the specific properties that they should be invertible and they should be differentiable. And you try basically to skew, right? You have a perfectly nice normal distribution or Gaussian field. You try to skew that distribution to become more complex, transform density. And once you learn this mapping, any random number you draw from this base density, it goes through the mapping, you get different realization for the transformed density. And in that case, you are basically using the model as generative model. And if you take the transformed density and you plug it back into the flow because the flow is invertible, then you basically get a probability because that's why it's an inference and it's a likelihood free inference technique. So with this, I had the pleasure to work with Roy. He's a PhD student in computer science in the Hebrew University of Jerusalem as a part of a machine learning school. And the basic idea, what we tried to do is that we wanted to ask the same question given our H1 maps. Can we actually, for a set of parameters, can we generate that? And as you see here, the camels is up. The model we call the H1 below, and then you see they look really visually indistinguishable, right, between each other. They look nice. You can, and the nice thing is that this is only to generate, but here's the thing that the diffusion model cannot really do, but normalizing flow can do, which is basically this is the posterior distribution coming out of this model. And you can actually do this in probably 2 minutes when you have a normalizing flow, and this doesn't take a long time to train. But this is very exciting because we have never been able actually for large scale map. We usually just look for the Bohr spectrum or look for PDF or something to process that. But now with these techniques, we are able to provide and constrain parameters coming out from high dimensional and large scale fields in a second, in a minute. And this is something revolutionary. It's something that transformative, something we have not been able to do before. And thanks to normalizing flow that we are able now to do this. So I think with that, this is my summary. I think artificial intelligence will be the future for, I hope that I managed to convince you that without AI, we wouldn't be able to actually to extract much of the information we have, because our models are more expensive, are very expensive. We need to explore different parameters, different realization. And without machine learning, especially when we come to these large scale maps and large scale signals, it's extremely hard to use the traditional methods to do this. And thank you very much for listening.
You're welcome. Thank you for the nice talk about this topic. And it's really good to know for all scientific from different majors to use an AI, because we can't avoid it. It's essentially now to all the students and research to know more about this kind of new technology.
Right.
Thank you a lot, Dr. Hassan, Sultan, sorry. And for anyone who want to have any questions, just raise your hand. أي حد عنده سؤال ممكن تفضل تفتح المايك على طول وتتواصل معنا. إذا في برضو أسئلة من الفيسبوك ممكن نبدأ بها أول على بال ما نشوف أسئلة الناس اللي معانا في الزوم.
ممكن عبر الفيسبوك ما في سؤال حتى الآن. في بس تحيات مرسلة للدكتور حسن من محمد إبراهيم يبلغك تحياته. ممكن أستغل الفرصة دي ولحد ما الناس تفكر في الأسئلة وكده أقوم أسأل. شكرا جدا دكتور سلطان على المحاضرة الشيقة والجميلة، سياحة مميزة جدا في عالم ال AI. عندي سؤال في الكامل اللي هو سيرفي اللي ذكرته في النهاية. عايز أعرف، هو طبعا مذكور إنه cosmology and astrophysics with machine learning simulation. So عندك فكرة إذا ممكن شخص عنده داري يعمل simulation أو يتحصل على معلومات في نطاق الانترستيلر ميديوم اللي هو a little bit like less small scale, how can I benefit from this? More in details, the question. For someone, for example, I had an opportunity to work in measuring the dispersion measure from the interstellar medium that going to affect the pulsar timing technique. Do you think this could be benefited in any way to get the properties or to understand the properties of the interstellar medium?
Yeah, thank you. That's a good question. I think it's the problem, as I said, these simulations are extremely expensive. So the simulation size is not big. It's only 25 megaparsec box each realization, but you have many of these realization. But the resolution is not high enough to actually resolve the ISM and to study anything about the ISM. However, you can, if you are able to think about an observable in a bit larger scale, right, that can connect to ISM physics, then you can do that. For instance, there are some people working on FRBs, right? So fast radio bursts, and they use the camels for that, and it's perfectly nice for it, and people publish papers with that. There are people also talk about work on Lyman alpha forest, right? So that's a very small scale signal, but they generate out of that liminal forest, right? And then they can study that. So if you are able to see, the nice things about this simulation is that for any set of these simulations, I can probably try to share a screen if we go to the website. But the basic idea, the website is here, but they are publicly available. The nice thing is that you have for each simulation, you have different cosmological parameters and you have different astrophysics, changing the stellar feedback and changing the black hole feedback. So that makes it very rich to look at things, but unfortunately the resolution is extremely low to be able to study, like to get the same, that this is what I showed in the beginning, right? To get this resolution in the ISM, to see the actual tiny details in parsec, no way, right? I don't think even the camels will have the resolution on this kiloparsec scale, because this is actually coming from TNG 50, which is one of the highest resolution simulation in the market. But the camels, I don't think you would be able to do lots of ISM unless you are able to define some observable in a slightly larger scale that is really connect you to small scale. And if you do so, then you can look at different parameters and the variation of how the feedback changes things and how the feedback would change the CGM or changing the IGM around it and stuff. And the nice thing is that they have the simulation for all different redshifts, I think from redshift of 6 and so. In the beginning, it was only Simba and Lister's TNG. Now they are there is the Eagle simulation already inside. Now there is also Astrid simulations. There are many. So, and I think like music as well. So I think like many of these simulations now are there. So it's a nice, it's very nice for comparing projects. I mean, the basic idea for the main idea for this Camels project was, if you care about cosmology, right, we don't know how to model the astrophysics, right? So the astrophysics is kind of unknown, right? We don't know, right? So, and the cosmologists, what they like to do, they want to run so many simulations with varying the astrophysics. I want to see whether they can marginalize over the astrophysics. And if you are able to marginalize over the astrophysics, then you don't care how to model the astrophysics, right? Like if I am able to vary all the simulation parameters with astrophysics, right? And changing the feedback, changing whatever, because we don't know, right? Like every model really models things differently. Like every model, like there are some models, they model star formation. If you have molecular gas, you have the star formation. If you don't have a molecular gas, no star formation, right? There are some models, they say, no, whether you have gas, but the gas has to be dense enough to be to form stars. And so different models do things differently, and this is very annoying to the cosmologist. So most of the cosmologists, they think, okay, let me vary everything, let me change everything, and let me try to marginalize over this. Like you can vary all the parameters, and then you try to constrain only for the cosmological parameters. And if you are able to recover good accuracy with the cosmological parameters, then it doesn't matter the way you really model astrophysics. This is the main motivation for this. But it turns out that these simulations are very useful for many things, and they are really cheap to download. You can play with them. I mean, anyone is really interested to use them. I have used them a lot. I'm very happy to help anyone interested in any project related to this camel simulation, because I think it's a very interesting set of simulations, and it's probably the first time ever happened in the field that we have training data sets from hydrodynamic simulation, because they are extremely expensive. Nobody can do this actually. And only the Flat Iron are able to do this because they are basically part of Simon's Foundation, which is non-profit organization where they have like lots of money to buy these high performance computing.
Thank you so much. It was an amazing answer. And yes, thank you really for bringing the fact that it could be used for the FRBs. It's very important for that, because
there is a group already actively working on this. If you are interested, I can invite you to the Camels Slack channel, and then you can connect to the people there, because there are already projects actually happening into the FRB side.
Okay. For now, my main focus was mainly in pulsar, which inside the galaxy. But yes, just it's very good to know about that. It's very
sure.
Nice.
Okay, Dr. Sultan, if you have the link with you now, you can share in the group chat. And also we have one question from Ahmed. He said, the opportunity for students and young research in the field of ML and astrophysics, and if have any opportunity in NASA for student now.
السؤال ده من دكتور بشير.
بشير, okay.
أعتقد.
So yeah, so this is one of the things I'm trying to do in my SNAP initiative, where I talk to the students a lot about how to find opportunities and to find opportunities for young researchers and students. Machine learning, it's still new in the field of astronomy, right? So now we are started to see now the emergence of machine learning centers and data science center in the universities, but it's less common in Europe, probably also less common in Canada, in Asia and in Africa. Also in the US, there are not lots of places do that. So, but now there is the emergence of lots of data science centers, which is very, very, very nice to observe now. And now there are many positions coming into this direction. So for NASA, particularly to join NASA, you can work. I mean, there is no specific program. I'm not aware of any specific program in NASA that really like machine learning and astrophysics and stuff. NASA has, of course, their own data science center mission, which basically monitor the data and stuff, and they have lots of software engineers and lots of data scientists working on this. But I think you might be able to work with people, right? Like similar to the students that they have been working with me. If you are interested in specific projects and specific machine learning techniques, you can always, the nice thing about astronomy, the field is really open, right? So you can reach out to people in NASA. I can also connect you to some people if you want. And then you can talk to them and try to start working on projects. But actual training in machine learning, usually there is lots of summer schools, there is lots of winter schools. If I see something, I usually share it with people. But usually if there is summer school, but specifically in NASA to have a summer school in machine learning or something, I haven't seen something like that. Most of their opportunities only just for like fellowships for research or just basically grants for applying for grants for faculty members and stuff. So for learning and training machine learning, I don't think they have any. I haven't seen something like that. But if you want to connect to NASA data science center and learning people in NASA, that's something easy you can do, because people are usually very open. You can actually just apply. You can email people and ask them about your interest, and people usually very, very friendly and very, very supportive. And now depends. If you are already good in machine learning, then you can identify projects with them. If you want to learn machine learning, then I think there are many avenues to do that through inter-school or summer schools, or you can do it probably also yourself online, right? I actually learned machine learning myself. I never been into like in a summer school or winter school or something like that. I just have been trying to watch videos online and read some papers and just look up some codes and that's it. But that requires a bit basic knowledge of like Python and like some programming language, but the rest should be straightforward to do. It shouldn't be that hard. Yeah. So that's good. The second question I see here, which is what is the possibility of applying these models to other fields? Yes, the nice thing is that actually most of these models are already in GitHub and they are already online, and you can, what we did actually, most of these models have been trained as they should, right? Like most of these models, machine learning models, that when they come in, right, you can see them have been trained on data set like this. This has nothing to do with astronomy and cosmology, right? But we take these models, we modify them. Sometimes we change them, right? We change them. Maybe sometimes we need to change them dramatically. But at the end of the day, it's basically a way to extract information from any image, right? And from any field. And if you have any fields that they are in any field you have in chemistry or in biology or whatever, if you have any data set that are very complex and you want to model them with these models, it should be very easy to do. I mean, like this model, the H1 Glow model, it's already in GitHub. People started to use it now for different kind of data set and different things, because the basic idea is that you can just replace the maps with different maps you want and replace the parameters with any parameters you want. And then you retrain the model again. And that is not really expensive. You might require, like it might be required to change a bit of parameters and different layers. But modifying the codes is easy because it's basically you can keep the same model. You have maps and you have parameters. If you replace them, and should be very easy to replace them in the code, then you can use these models easy in different part of the in different fields. Of course, that should be very doable. اوكي.
في أسئلة على الفيسبوك ولا ما في؟
حتى الآن ما في سؤال على الفيسبوك.
معناها الناس فاهمة أي حاجة، وده كلام جميل جدا جدا.
في سؤال على الشات تقريبا تاني.
ML models limited. I didn't really get the question exactly.
How machine learning models limited theoretical developments.
ما فهمت السؤال exactly. What does this mean?
يعني أعتقد هو بيقصد هل النماذج اللي اتعملت في الماشين ليرنينج هل أثرت سلبا على التطور الثيوريتيكال aspects اللي هو ما أعتقد.
So that's a very interesting question, and that's actually also like talk to many. So there are many people think that this is very connected to the question of whether did we really discover anything new with machine learning or not, and that's a big debate in the field, whether we are really able to discover that or not. Okay, so my answer to that is that first of all, machine learning can give you different view of things, right? Like you can have your theoretical development and you can have your models, right? But machine learning is able to take any problem you have into a different space. And in that space, you might be able to see things that you are not able to see with your theoretical models, right? That's first thing. The second thing is that I do believe that all these models and all these machine learning models, because you basically machine learning, you're trying to learn a mapping between different things, right? And that mapping is really rich. And any one of these models, it has million of hyperparameters you tune, right, to get to the right answer. One of the things that we are not really good at, and it's an active research in machine learning too, which is how learning is really happening, the interpretability of machine learning models, and the representation that is learned by these models. What do they capture and what do they mean, right? And that's why most of these machine learning people just use them as black boxes. And we need to open the black box. We need to open these models. We need to understand these models, and we need to be able to understand why the learning happens the way it is. And if we are to do that, I'm pretty sure because of the information in these models, we would be able to discover things that we never seen before. So far, machine learning is in the field is very good at speeding up any calculation you want, right? So if you are interested, like, okay, so I start with density field and I evolve things and I form dark matter halos and galaxies and AGN and stars and all these things, and I evolve this from the early universe till now, right? But at the end of the day, I'm not really interested in all this journey. I have only one signal I want, right? Which is that signal, either like a star formation, fluctuations, or like how the star formation happening, or what the feedback, or what is the luminosity functions, like how many galaxies are there. So I'm interested in that signal only. And if I am interested in that signal, if there is a way for me to get to that signal very quickly, then that's really enable many studies, and it tells you, it will help you to explore different parts of the parameters you cannot do because your simulation is very expensive. So for speeding up the simulation, it's an amazing tool. But the interpretability is hard, and I also started recently to work on this. We don't have time. I could have talked about different projects on that. But I think if we know, if we are able to interpret machine learning models very well, I think we would be able to discover a lot. And I don't think it limits any theoretical development. It's basically, we use it as a tool to help us to speed up calculation, to speed up anything. We still, this camel simulation, right? We are doing this. One of the question you can ask me, well, I mean, the camel simulation, Simba and TNG, they are not the ultimate reality. We don't know whether Simba is right or TNG is right. And any machine learning model you train on this camel simulation is useless, because we don't know whether these models really capture the truth, right? Because they are completely different. But they are different, but they really reproduce the same observation, which is one of the interesting things about this. But then you can ask me this question, but we need to be able to make this proof of concept, right? Like, even if we don't have the data set and we don't believe this simulation, we need actually to make a proof of concept. We didn't know whether diffusion models will work for this. We didn't know whether normalizing flow will work with this. But now we are able to do that. We should demonstrate that it works. Now, once we have improved models, that's why in the beginning I said, let's just assume that our models are improved already. But now, if you have this camel simulation, and we are working actively to modify their models and to improve the models of within these simulations. But once we have our improved models, it should be an easy change to the code, and easy change replacing the maps and the parameter to get different realities and different distribution, right? So so it does not limit that. It's still, there is active people still need to improve the astrophysics, because as I said, as you see here from these things, this is something we can, there is no model is able to capture this in sub-parsec scales on this extremely large scale. So we really need to be able to do this, and there are many ways. We will debate this, how to do this and how to do that. But without doing this, without including all the physics we have, you should have parameters changing the astrophysics in the stellar medium. You should have parameter changing the circumgalactic medium. You should have parameter changing the intergalactic medium. And then now you have different physics coming from the medium between stars, medium between galaxies, and medium nearby galaxies. And that will give you lots of information to extract from. So this is still an active field of research, and I don't think it limits that. But most of the people that are really skeptical about machine learning, they have that way of thinking, is that machine learning is not really helping us a lot. But for me, from what I have seen so far, there is no way you can analyze these large scale maps when they come in with just traditional methods, because MCMC or any Bayesian method will just break down. You run out of memory. That's it, done. So I think that's the basic idea.
There is a follow-up question.
So for students and beginners, I think that's a good question. So the basic, I mean, most of the machine codes now, our software packages like TensorFlow and PyTorch and others, they mainly in Python. So you need to have some limited understanding, like some basic understanding of Python. So you should be able to know how to write a Python code and to compile to run the code and to do simple stuff like for loops and simple analysis and reading file and outputting file. These are very small tasks you should be able to do. And then after that, I think once you have that basic, I don't think it's really hard. I can share some resources about this. But my start with that was just there is an I can let me see if I stop sharing and I can show you something now, which is very let me see here. I will show you what I actually did, and that's it. Okay, so let me see if I can share a screen here. So this is my start point was learn deep learning without PhD. Okay, and this guy is really he's a software developer in Google, and TensorFlow of course is coming from Google, and is basically if you it's just a video, you find it in YouTube. You can watch it, and you can watch it, and then you have the slides here. And he walks through, like he walks slowly and nicely about what machine learning is, what the calculation you can do. I think it's a very, if you look it up, just if you write like machine learning without PhD, that was my start. He talks about the different things, and I don't think you really need some explanation to this. He really writes this very nicely, and I think if you just come back up to chapter 6 is okay. The problem with this is that it's still TensorFlow, but most of the people now going into PyTorch, so that makes it hard. But like for the basic understanding of deep learning, I think this is an extremely nice blog which shows, it takes you about simple task of neural network and how do you do classification between numbers and stuff. So it's a very easy to follow. It's a video about like 3 hours or 2 hours and a half or something. So you can watch that, and I think this is what I started with. And but I myself, I was already doing lots of Python before, so I know lots of Python. But I think if you have just the basic minimum things of Python and you watch this movie, like these videos about deep learning without PhD, because he makes it very nice. It's a 3-hour course, as he say here, 3-hour course, and he has the codes already available, so you can just download the code and talk about it. So I think it's a good place to start. Okay, happy everybody? Happy.
شكرا جزيلا دكتور. بالنسبة للناس اللي هيحضروا دخلوا متأخر أو عندهم مشكلة في النت واللي هيحضروا المحاضرة بعدين بيلاقوا المعلومات كاملة وكيف يتواصلوا مع الدكتور مع بداية المحاضرة إن شاء الله.
Yeah, no, thank you very much for that. It was really fun to be here, and I wish Photon luck.
ممكن أتدخل؟ إيهاب؟
ممكن أتفضل.
شكرا دكتور حسن على المحاضرة الجميلة. عايز أنوه إنه إذا في أي resources المنصة مفتوحة بالنسبة لك، تشاركها مع beginners، مع الناس المهتمين بالمجال. feel free إنك تنشرها على المنصة. حنكون
قصدك على صفحتكم في الفيسبوك،
على الصفحة أو على المجموعة تحت الواتساب. يعني ما شاء الله في ريسورسز كويسة already موجودة حاليا في المحاضرة دي، فدي بتتبع كويسة. لكن إذا في أي ريسورس ثانية حاسس إنك عايز تضيفها، it's very welcome. عايز أضيف برضو حاجة تانية، حنكون برضو سعيدين جدا إنه نساهم إذا في أي حاجة ومتطلبات في الانيشيتيف تبعك سناب. إذا شايف المنصة ممكن تفيد بأي شكل كان. we are very
والله طبعا انا اكثر حاجه هكون محتاج لها يعني هو واحده من المشاكل الكبيره حاليا لما تقدر تقدم لجرادويت سكول ناو برا، مش كده في امريكا ولا اوروبا ولا هناي. الموضوع بتاع تكتب الموتيفيشن بتاعك بتاع انه انا حابين دريمينج بستارز من انا شافع صغير وكنت بحلم بالنجوم، الكلام ده بقى ما شغال. فهمت؟ بقى بيشتغل الكلام ده. الناس دايره الريل ريسيرش اكسبيرينس، دايره الريل ريسيرش اكسبيرينس، دايره طالب to demonstrate that انه هو he is able to عنده technical skills, he worked on specific projects، يا حبذا يكون عنده publication عديل. وانا انا الحال خلتني افكر في الحاجه دي بالتحديد، لانه انا يعني المشكله نحن بس ناسنا ما يعني السودان ناس ما بيعرفوا، ما عندنا المعرفه بتاعت الفرص بتجي كيف وات از نيدد وات از ريكوايرد، وي دونت نو صح. وانا بفتكر نحن كلنا وي هاف بين جاست لاكي رايت، نحن ما عملنا حاجه عظيمه، نحن هاف بين جاست لاكي تو بي ايبل تو جيت يعني منحه وحاجات تطلع، لكن نحن ما ناس يعني شفاته ولا شطار ولا كده عشان ينانا. فبالتالي نحن وي هاف بين اكستريم لاكي. وانا لما بكون قاعد يعني الحاجه يعني بلقى مثلا يعني القى ايميلات من طلبه من الهند ولا من امريكا ولا من كندا ولا من اوروبا، بيكونوا طلبه مثلا يا دوب اندر جراد او هم يا دوب يعني تخرجوا يا دوب و they looking for PhD positions و they email me they want to work on experience يعني research experience and I never thought I never realized why they do this. يعني الناس دي ما يمشوا يستمتعوا بحياتهم وما لهم داري يمعطوا روحهم من هسي يعني. ففي النهايه اكتشفت لما اتكلمت مع جميع الكوميتيز والسلكشن كوميتيز بتاعت الجراديويت سكول وكده، لقيت انه هم عارفين الجيم، عارفين انه الكومبيتيشن صعب، وعارفين الجيم انه هم they need to add something real to their CV. So they need to say that we have worked with this or we worked with this, we worked on this and hopefully they can publish something, you know. يعني انا recently في واحد طالب من الهند ده زول طالع من undergrad لكن السكيلز اللي عنده it's impressive and we had already paper published out. And even all after this, he was not able to get a PhD last year. So he started to contact other people and to have a much higher profile. So I think the challenge نحن عندنا إنه نحن ما الطلبة بتاعيننا في السودان they are not aware about this. كويس؟ ما في واحد فيهم بالنهاية بس بيفتكر إنه الموضوع ديجريز، بس إنك أنت تمشي تعمل ماجستير وتقدم وكده صح، لكن عشان تنافس برا في الجامعات وفي الحتات الكبيرة وتلقى لك منح وتلقى حاجات كويسة. وطبعا أي محل بيفتح بيكون في 100 ابلكيشن ولا 200 ابلكيشن قاعده. فواحده من التشالنجز انه هم they have to stand out of this application pool and the way you stand out is by showing an actual research experience. ودي واحده من الحاجات اللي انا ساعي اعملها يعني. انا we still just started يعني we had only 2 sessions before we talked about how to apply for graduate school, how to write motivation letters, how we started like with simple mathematics which is like how to do linear regression and stuff. لكن my plan and my hope is by I don't know يعني by February or March or something is we transition into an actual research experience. We can define a very basic projects to work on, and I already have 6 students there, and I have already my own other students like I have like maybe like another 7 or 6 students, so I'm already overwhelmed. So I might not be able to work with all of them. So it would be nice يعني مثلا انت هسه في مجالك بتاع البلصار ده لو عندك any simple ideas, simple analysis, ان شاء الله يعني just plotting histograms and doing very simple stuff, right? If you have any data or anything or any work that you can propose to someone to redo the analysis or to do something new, ما بالضروره يكون machine learning، ما بالضروره يكون statistic، يعني anywhere right you think that might be very easy you can supervise, you can do in maybe like a matter of 6 months. The hope of course انك انت تبلش الحاجه دي، لكن it might be hard. لكن هم through this experience they can say it in their CV. And at the same time one of the things is that the recommendation letter, right? So the recommendation letter is that when they work with you, you can write to them more personalized and strong letter, right? Because now you are able to see them much more. And دي واحدة من التشالنجز اللي عندنا. نحن ما عندنا unfortunately ودي حاجة حزينة، نحن ما عندنا ناس في السودان بيكتبوا recommendations letter كويسة يعني. الكلام ده تعميما probably على كل الناس يعني. ما عندنا ناس. وانا قبل كده في ناس كتبوا لي ريكومنديشن، ادوني بس الريكومنديشن كانت تمبلت جاهزه، بس شال اسم الزول القديم وخط اسمي بس، فهمت؟ ودي ريكومنديشن لما تجي يشوفوها اي محل بتبقى مشكله كبيره. في ريكومنديشن يو كان سي ات هاز فيري انجلش بروبلم، يعني فيها انجليزي مشاكل بتاع انجليزي، وبالتالي دي حاجه ذاتها بتكون يعني ما كويسه مع الطلبه. فانا الحاجه اللي بحاول اعملها انه الطلبه ديل يقدروا يلقوا كونكشن مع researchers like you and me and anyone is in the field and they work in real experience. I might also invite other collaborators of mine to come and talk to them so they can also get so الهدف اللي انا ساعي له شنو؟ انه هم they are able at the end of the day to be able to compete to get a nice positions. لكن نحن we working on the basics: how to write motivation letter, how to apply for the schools, where to find the graduate school, and how to make a nice CV. And the nice CV is that requires you to work on actual research experience. And people do that even from the undergraduate. يعني undergraduate they are working on research experience. يعني هسه مثلا جامعة نيويورك اللي أنا فيها دي هسه عندهم برنامج اسمه كابستون. الكابستون بروجكتس دي كريدت عديل، يعني الجامعة بتديك عليه كريدت part of your certificate يعني. وبالتالي كابستون انك انت you work with faculties or postdocs or anyone around and for مشروع ل one semester كامل بخلوك تقرا فيه، وفي النهايه لازم تعمل برزنتيشن فيه وتعمل بوستر فيه، وبعد ذاك الطلبه if they are interested they can continue working with you and they can publish it later. if they are not interested they can just stop it. لكن هم الحاجه دي بيعملوها لاسباب كثيره. اول حاجه بتوري الطالب ذاته هل انه انا الريسيرش ده بقدر عليه او دايره ولا ما دايره. ممكن اكون ما داير الموضوع كله وما وريت روحي في بيت شديد نهائي، وممكن الموضوع يعجبني شديد، والموضوع ذاته يدوك احساس انه انت ماشي على بيت شديد وانك انت مفروض يكون عندك سم اكسبيرينس. فده اللي بيعملوها هنا ناتشورالي في الجامعات. لكن الحتات الدول الثانيه زي الهند وزي وين الناس اللي ما عندهم، السودان اوبفيسلي في اسيا وافريقيا والحتات اللي ما عندهم يقول لهم ريسيرش اكسبيرينس، they have to contact people. So students what they do is that they send randomly email to people, so you either respond to them ولا ما respond to them, and then they try to work hard as they can to interact with people and to attend conferences remotely and to work on real experience. So then they can write it, they say whatever, and then when you apply for a PhD position, because there are many people, they look, oh, this guy already has done a lot, right? Like he has already research experience. He would be a very valuable member to our department. Let's take him or let's take her, right? So I think that's what I'm aiming to do. So I might ask many of you, anyone is interested, of course, I would be happy to, if you have any project, even if you don't have a project, I could define many projects and we can work together on that. But as I said, it will be very hard for me to lead all the projects with the students, and then you can do one-to-one, and hopefully that would be very useful to them. At the end of the day, just we are trying to maximize their chances and their CVs, right? and ونحن بس كنا lucky، لكن نحن ممكن نحول اللك ده لحاجه ترو، حاجه حقيقيه، لما هم يكون عندهم معرفه ونوليدج ويكونوا عارفين الفرص بتجي من وين والمحتاجين شنو. ديل التشالنجز بتاعتنا، لانه انا بتذكر نفسي زمان نحن بس بنشوف ديل والله قدموا لامس راح نقدم لامس، ديل قدموا كده راح نقدم كده، ديل قدموا كده، ونحن لاكي بس بتشوت ابلكيشنك دي وما معروف غايته تجي ولا ما تجي، صح؟ فتلقى لك فرصه ولا ما تلقى فرصه. لكن دي ما الحاجه اللي نحن مفروض الطلبه في السودان، ونحن كمان في السودان براو فيه حزن تاريخي، لكن الاغلبيه يعني قدروا، يعني اغلبيه الطلبه اللي معاي ديل قدروا يطلعوا من السودان. لكن unfortunately الناس اللي قاعده في السودان، وهوبفولي يعني الحرب دي تقيف والامور تبقى احسن.
شكرا. بس عشان نضع الحديث الجميل ده في الكونتكست، يعني دكتور سلطان بيتحدث عن في البرود كونتكست بتاعه عن سناب، وده برنامج هو الفاوندر له، زي ما بقولوا سمح الكلام في خشم سيدي. وإذا عايز تضيف تعريف مختصر في أقل من دقيقة أو دقيقة عن سناب يا دكتور، تعرف بيه الناس عشان يكونوا عارفين إنه الحديث المطول ده كان عن البرنامج.
ما هو سناب ده بس اختصار ل الايدياز كلها جاتني as ما was saying انه how to help the Sudanese و next generation of astronomers, so the program called Sudan Next Astronomer Program SNAP, and this idea just came into how to train the next generation of astronomers from Sudan, and how do we واحدة من الحاجات بتاعتنا نحن we are very العالم is very diverse. البريزنس بتاع السودانيين في المجالات بتاعت العلوم المختلفة is very 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 low. And whenever I go, I always find people, oh, you are probably the only African or the only Sudanese I met so far. So I always find myself the only guy. في الكونفرنسز والworkshops والحاجات probably you experience the same. So نحن how do we really maximize our presence, right? يعني في مجال العلوم كلها. يعني أنا حاولت to design البرنامج بالنسبة للأسترونومي لأنه this is where I have experience. لكن I think we can extend this program to target other audiences, right? Like anyone who's want to do chemistry or any sciences, right? حتى لو ما ساينس، لانه نحن في النهايه لما انت تتكلم عن حاجات معينه اللي هي الريسيرش، وتتكلم عن how to apply, how to write cover letter, how to write motivation letter, how to make a nice CV, what is needed to show in every single، يعني الحاجات دي كلها حاجات ممكن تعمم للناس. لكن انا حاولت اختصره بس على الاسترونومي لانه this is where I can define projects and I can work as hard as I can to help the people going into the astronomy. فهو بس initiative بدينا اللي احنا لنا شهرين يمكن ولا شهر كده. عملنا 2 sessions. السيشن الاول كان تعريفي، عملنا 3 سيشن. السيشن الاول كان تعريفي، السيشن الثاني كان بيتكلم عن how to apply for graduate school and some linear regression tasks. السيشن الثاني برضو تكلمت عن how to write motivation letter وكده. ف وكل الكورسز هي يعني كل الحاجات اللي انا الكلام اللي انا السيشنز اللي عملناها recorded already. I could share the YouTube link for them, for anyone interested to watch them. لانه في الكلام بتاع how to apply for graduate school or how to write motivation letter that would be probably general to everyone, so not only for astronomy. ودي الفكره الاساسيه. ففي الغالب الواحد اللي قدام لما يجي المرحله بتاعت انه داير يعني يدخل الطلبه في actual real experience بتاعت projects, it would be helpful to know. يعني لو في ناس من المركز بتاع فوتون هنا interested انهم to supervise. انا تكلمت مع بشير قبل كده في الموضوع ده. If anyone is interested to advise students, and I افتكر also is very good for you, right? Like it's very good for you as a PhD student or as a researcher anywhere, right? To have a mentoring experience, right? So it's really good. I don't think it's very bad. So you can think about it, think about ideas for projects that you can do quickly, and then we can have the students to work on them. I think this would be amazing because now you will get experience. It's something, I think it's a win-win case for everyone. It's something good for your CV, something good for their CV. Everybody will win. So that's the basic idea.
هتكلم معك ان شاء الله في الموضوع ده.
Sure.
لكن very promising فعلا. انا طبعا متابع التحديثات اللي بتنزلها انت على الفيسبوك.
Right.
initiative ممتازة شديد. في تعليق من الدكتور بشير ذكر انه هو مع الدكتور حسن عندهم خطة plan to have sessions to show students how they can be involved in doing research and activities and research experience. ودي حاجة برضو احنا حنكون مستضيفينها ان شاء الله في عبر المركز، ودي حاجة كويسة. فهي في النهاية زي ما قالوا كلها خطط بتدعم بعض إن شاء الله.
لا 100% تمام.
أنا ما عندي حاجة ابتهال من جانبي.
أعتقد خلاص الأسئلة انتهت. نشكر الدكتور مرة تانية على المحاضرة القيمة، والناس اللي عايزين يستفسروا أو ما حضروا المحاضرة حيلاقوها مرفوعة على الفيسبوك. وإن شاء الله لو عندكم أي أسئلة ممكن تتواصلوا مع إيميل الدكتور مباشرة أو تدخلوا الأسئلة في الجروب في الواتساب أو الفيسبوك إن شاء الله. شكرا جزيلا، إن شاء الله نلتقي المرة القادمة على خير، والسلام عليكم.
شكرا جزيلا.
شكرا جزيلا.
السلام، باي باي.